Today we're going to talk about the quotient rule, how to find the derivative of a function that is a quotient of two others. So let's start with a derivative, a function that is a quotient of two others. H of x is f of x over g of x. Now we can of course rewrite that as f of x times f of x times g of x to the negative first, or the reciprocal of g of x. In which case it now looks like a product, which we are familiar with. So we can find the derivative of that quotient using the product rule. So we will take, and I'm going to use a little bit of color coding here, f of x is what we'll call the first function, g of x is what we'll call the second function for our product rule. And so h prime of x would be the derivative of the first times the second plus the derivative of the second. I'll say this first plus the first without the derivative times the derivative of the second. And this one does get a little bit complicated. This is where we need to use a couple of different rules. G of x to the negative first, remember that's a composition. That is a function, g of x, inside of another function, the reciprocal. So to take the derivative of that, it is a little bit complicated. We need to think about the outside first, so that's bring down the coefficient, bring down the exponent as a coefficient, times g of x to the negative second, times the derivative of the inside, which is g prime of x. So here we have the derivative of the first times the second plus the first times the derivative of the second. And we'll clean it up just a tiny little bit. So that is f prime of x over g of x plus f of x times g prime of x over g of x squared. And then you'll notice that those two fractions have almost the same denominator. So what we can do is just adjust this guy a little bit, multiply by 1, so that the denominator of both fractions in that derivative are g of x squared, and so then we can put it together. G of x times f prime of x. Notice I made a mistake above. I forgot about this little negative sign right here, so that would carry on. So minus f of x times g prime of x over g of x squared, and that is the derivative of our quotient function. So that makes a rule. That is the quotient rule. Putting it in words is quite wordy. I don't really want you to be thinking of it this way. I do have a cool mnemonic. I don't know why this has stuck with me over all these years, but I remember learning it this way when I was learning calculus. The mnemonic for the quotient rule is low d high minus high d low over low low. When I say low, I'm talking about the denominator, right? Because it's, sorry, I said that backwards, because the denominator is the lower part of the fraction, and the numerator is the higher part. So the quotient rule is the low, so that's the denominator, times d high means the derivative of the numerator, minus high d low over low low, that's the low squared. So that's what that low d high minus high d low over low low means. If that helps you remember it, that's fantastic. If not, that's okay also. Let's just see it in action a couple of times. So to find the derivative of f of x here, we need to take low d high minus high d low over low low. And I don't really want to touch that denominator. I will clean up the numerator just a little bit. There's not a ton to do here, but I will at least put the 5 first. 5 cosine x times 8x minus 3 minus 8 sine of 5x all over 8 minus 3 squared. 8x minus 3 squared. There's no reason to FOIL that out. Just leave it the way it is. And that's good enough. For the next one, y prime. This one, there's going to be a little bit more cleaning up to do. But the structure, the way we set it up, is the same. Low, d high. With the d high, there's a little bit of a chain rule to remember here. It is 5x minus 2 to the 7th, so it's 7 times 5x minus 2 to the 6th. But remember, because of that 5 in the 5x minus 2, we also have the derivative of the inside to worry about. So just a little bit of color coding. This was the high. This whole thing here was the derivative of the high, the derivative of the numerator. We'll keep going. Minus high d low. The derivative of the denominator is going to be very similar to the derivative of the numerator. First, we'll use the power rule. And then, of course, because the inside function, that 4x plus 9, has that 4 times the derivative of that also, all over low. And I can write 4x plus 9 cubed squared. That's a little bit silly, so I'll just write 4x plus 9 to the 6th. And if you leave a final answer like that, that's fine if it's open-ended. Just bear in mind, you're not going to see that big mess of a thing as the choice on a multiple choice question. So you do need to be comfortable cleaning it up a little bit. So I'll start with just saying the whole thing over again, but pulling my coefficients in front, because that's a little bit easier to see. So 35 times 4x plus 9 cubed times 5x minus 2 to the 6th minus 12 times 5x minus 2 to the 7th times 4x plus 9 squared, and all of that over 4x plus 9 to the 6th. And if you look in the numerator, you'll see that there are some things I can pull out. There are 4x plus 9s everywhere. There are 5x minus 2s everywhere, so I can do some pulling out. I'm going to factor some. I'm going to undistribute as many 4x plus 9s as I can. In the numerator, the first term there are 3 of them, and the second term there are 2 of them, so I can pull out 4x plus 9 squared. And for the 5x minus 2, in the first term there are 6 of them, in the second term there are 7, so I can pull out 6. And after I'm done pulling those out, undistributing 4x plus 9 squared times 5x minus 2 to the 6th, in the first term I'm still left with the 35, and I pulled out all of the 5x squared, so those are gone, but I only took out 2 of the 4x plus 9, so there is going to be one of those left. 35 times 4x plus 9. And from the second term, the negative 12 is still there. I pulled out all of the 4x plus 9s, those are gone, and I pulled out all but one of the 5x minus 2s. So there is still going to be a 5x minus 2. And that's all over 4x plus 9 to the 6th still. And 2 last little things I can do here. Number 1, 4x plus 9 squared over 4x plus 9 to the 6th can reduce. So I can make that 4x plus 9 to the 4th. And in the numerator, the 5x minus 2 to the 6th is staying put. But I can simplify everything that's in here. If I distribute the 35 times 4x is 140x. And 12 times 5x, or negative 12 times 5x, is negative 60x. So if I put those together, that is 140x Actually, I'll write it out the long way first. 140x and 35 times 9 is 270 and 45. So that's 315. Minus 60x plus 24. So I can do one last, I'm just going to group all of this together so I can shrink it a little bit. Give myself a little bit more room here. And so I can write this one last line here. I can put together these last two terms, 5x minus 2 to the 6th that's staying put, but 140x minus 60x, and 315 plus 24. And this is one long, tedious process to get a derivative. I do want to show you real quick a reminder, just you can check your answers on derivatives. I'll check it up from the first one. Remember how it works. You type in f of x the way it was in the problem, the sine of 5x over 8x minus 3. And I really don't care what that graph looks like. I'm not even going to look at it. I'm just going to turn it off. My answer was kind of long, but it was 5 times the cosine of x times 8x minus 3. I put those parentheses in there so that Desmos wouldn't get confused about where my cosine ended. If I wanted to, I could just do it like there, and that accomplishes the same thing. And then it was minus 8 times the sine of 5x, and that was all over 8x minus 3 squared. And again, I don't really care what that looks like. I just want to know, is that the same thing as f prime of x? So looking back really carefully at what I did, where did I make a mistake here? Oh, this is a simple one. This is the sine of 5x, which means when I take its derivative for low d high, it's the cosine derivative of the outside evaluated at the inside. I forgot my evaluated at the inside. I left off a 5. So now you can see that derivative that I got my answer and the derivative just by using f prime is the same graph, which that's a good sign. That means we did the work.